You ever look at a giant skyscraper and wonder, how on earth does that thing stay standing during an earthquake? I mean, it seems impossible, right? A rigid structure against a force that's pure chaos? Well, it turns out engineers have a seriously clever way to tackle this problem. So how do they do it? Let's get into it. Okay, so first, you have to really appreciate just how complicated this problem is. An earthquake isn't some simple push from one side. No, the ground is shaking forwards, backwards, side to side, and even up and down, all at the exact same time. So this is the million-dollar question for any structural engineer. How in the world do you design for that? How can you possibly calculate the forces when the ground itself is just a mess of chaotic motion? The math alone seems like it would be a total nightmare. Well, when the going gets tough, great engineers find an elegant shortcut. Instead of trying to model every single little chaotic movement, they came up with something much, much simpler and way more practical. And this right here perfectly shows the big idea. On the left, you've got the reality of an earthquake, all that chaotic, multi-directional shaking. But on the right, you see the engineering solution. They found a way to convert all that complex motion into one single equivalent push to the side. It's like turning a wild scribble into one clean, straight line. This brilliant little trick has a name, of course. It's called the Equivalent Static Method, or ESM for short. And it is, without a doubt, one of the most fundamental tools in seismic design. The key word here is equivalent. It's not the actual force, but it's designed to have the same overall effect on the building. Pretty clever.
Now, hold on. This powerful shortcut isn't a one-size-fits-all solution. You can't use it for every single building. It's specifically designed for the most common kinds of structures out there, buildings that have a pretty regular shape and aren't super tall. Think about your typical school, apartment block, or office building.
So, the next big question is, if we're going to replace this whole complicated earthquake with one simple push, how big does that push need to be? Engineers call this total horizontal force the base shear, and figuring that out is the next crucial step. It all boils down to this simple-looking formula. Now, don't worry about the letters. The concept is actually really intuitive. The total push, which is VB, is just the building's total weight, W, multiplied by a special number, AH, that basically acts as an earthquake risk score. So really, it's just weight times risk score. Simple as that. Let's break that down. First, the weight, W. This is pretty straightforward. It's the total weight of the structure itself, all the concrete, steel, and walls, plus a little extra for the stuff we expect to be inside, like furniture, equipment, and people. It makes sense, right? Heavier buildings have more inertia, so they're going to attract more force. Okay, now for the really clever part. The best way to think about this is as a custom seismic risk score for that specific building in that specific location. It manages to wrap up the entire earthquake threat into one tidy number. So what goes into this risk score? Well, it's a mix of 4 key questions. First, where is the building? Is it in a high-risk zone? That's the zone factor. Second, how important is this building? A hospital, for example, needs to be way safer than a storage shed. That's the importance factor. Third, what's it built on? Soft, jello-like soil is way worse than solid rock. And finally, how is the building itself designed? Is it flexible and built to bend without breaking? That all gets combined to create that one powerful number. So let's make this feel a bit more real. For, say, a typical 3-story concrete building in a pretty high-risk earthquake zone, once you do all the math, that total push, the base shear, might come out to something like 360 kilonewtons. Now, that's a real number, a tangible force engineers can actually design for. Okay, so we've got our total push figured out, but we can't just apply all of that force at the bottom of the building. That wouldn't be realistic. We need to spread that force out along the height of the building to mimic how it would actually shake. The process is pretty logical. Step 1, you calculate that total push, the base shear we just talked about. Step 2, you divide that total force up and assign a piece of it to each floor. And step 3, and this is super important, you don't distribute it evenly. You actually have to apply more force to the floors higher up. And this chart shows you exactly why. Think of a whiplash effect. When an earthquake hits, the top of a building swings back and forth way more dramatically than the bottom. So to account for that, engineers assign a bigger chunk of that total force to the upper levels. You can see it right here. The 3rd floor has to take the biggest hit. Look, the equivalent static method is incredibly powerful, but we have to remember, it is a shortcut. And when you're dealing with very tall buildings or structures with weird, complex shapes, a shortcut just isn't going to be enough. You need to bring out the bigger tools. This table really puts it all into perspective. Our ESM method is the go-to for regular, low-rise buildings. For anything more complicated or taller, engineers step up to more sophisticated methods. And for the really critical stuff, the world's tallest skyscrapers, major bridges, they use the most complex analysis of all, a time history analysis, which is basically a full-on computer simulation of an earthquake, second by second. And this quote right here gets to the technical heart of why that is. The ESM is brilliant, but it really only captures the main, fundamental way a building sways. Tall and irregular buildings have these complicated higher mode effects, meaning they can twist and bend and shake in multiple different ways all at once. And to capture that kind of complex behavior, you just need a more powerful analysis. So after all that, what's the big takeaway? It's easy to get fascinated by the super complex methods for giant skyscrapers, but we shouldn't forget just how important this foundational approach really is. And that's really the bottom line. The equivalent static method is the unsung hero of earthquake engineering. It's this beautiful, elegant simplification that turns a ridiculously chaotic problem into something manageable. It's the reason that the vast majority of our everyday buildings, the places we live and work and go to school, can be designed safely and efficiently to stand strong when the ground starts to shake. It really is a testament to brilliant engineering. And it kind of leaves you with one last thought, doesn't it? If this is the clever shortcut we use for all our normal buildings, just imagine the incredible, complex, invisible forces that engineers have to account for when they're designing our world's tallest and most iconic skyscrapers.